This is a production of Cornell University.
So today we're going to be examining the physical properties of soil. And as we mentioned before, most of soils are made up of three particle sizes: sand, which is the largest size; silt, which is a very small size of sand, if you could think of it that way; and clay, which is the very smallest size particle, which is wafered and cannot see it to the naked eye. So the way those particles come together, sand, silt, and clay, gives us the texture of the soil. Texture is actually the percentage of sand, silt, and clay in any particular soil. Why this is important is that the way the particles come together give you the porosity, the amount of pore space that allow water to move in the soil. And so this demonstration is aimed at showing you how water moves in different textures, if you like, of soil, using sponges as proxies for soil. And as you can see, this kitchen sponge is just, it's got pore space, it's got solids, it's got air, which is a good proxy for soil, which is about 50% solid, 25% water, and 25% air in an idealized situation. So we can use these sponges with different pore sizes to tell us how water moves in soils. So what I'm going to do here first is take this kitchen sponge and I'm going to put it underwater and squeeze all the air out of it. And then I'll let it open underwater. And then I'll bring it up into the air. And the point where there's no more air in the sponge but just water is called saturation. Now, saturation is when all the pores are filled with water. But of course, as soon as I bring it out of the water, it starts to drain via gravity. Gravity is pulling the water from the sponge down. We've still got plenty of water in the sponge, but it's not, even though gravity is still there, it's not being able to pull more water from the sponge. At that point, if we could assume that these drips have stopped, we call that field capacity, which is the amount of water a soil can hold against gravity, basically hold within its pores. So we have basically, this is field capacity now. Basically, most of the water is gone. Free water is gone via gravity. When I mean free water, it's the water in the big pores, which are called macropores, that are free to move via gravity. The water in the small pores, called micropores, are holding onto that water so that they're not able to be taken away by gravity. So then I say, this field capacity, this is the amount of water this sponge or this soil can hold. If we want to say, well, now it's able for the roots to get that water from the soil, I'm going to pretend I'm a root, but I'm just going to squeeze the sponge. So I'm a root getting the water from the sponge, which would be via osmosis, but we're just pretending. So I'm just squeezing the sponge until I can't really squeeze any more water out of it. And there's still plenty of water in this sponge, as you could all imagine, but it's held so tightly by the pores that roots are not able to get that water by osmosis. And at that point, we call this the permanent wilting point, where the soil has water in it, but it's held so tightly that roots cannot get the water. So between field capacity, which is after gravity drains the free water away, and where I've squeezed the water and you cannot get any more water off of the sponge, we call that the available water holding capacity of the soil. That's the amount of water any particular soil, and it varies from soil to soil, can hold against gravity and was holding so tightly in the pores that roots can't get it. So different soils have different available water holding capacities. And I'm going to take this other sponge here, which is a yellow, really big pore sponge. You can see this sponge here. It's much more open than the orange sponge. I'm going to open it underwater again, as I did with the orange sponge, squeeze all the air out, let the water fill the pores, and I'm going to see what the So much more water is coming out via gravity than the orange sponge, because there's lots of big pores which allow gravity to pull that water down. The small pores hold the water. The big pores allow the water to go down. And then if I were to squeeze this sponge, there's not very much water that's actually left in it. And in fact, the available water holding capacity of this sponge would be much less than this sponge. So why is there still water left in the sponge after I squeeze it? That's because of the forces of adhesion and cohesion. Cohesion is the attractiveness of water to itself. Water tends to bead up when it's on a surface. But adhesion is the attractiveness of a solid surface to water. And this is critical when you have small pores. There's lots of forces of adhesion holding the water in the pores. Where you get further and further from a solid surface, like in a big pore, the water is then able to move via gravity, because the forces of adhesion are being overwhelmed by the fact that the water is further away from the solid surface. It's interesting to look at some different types of sponges to see what kind of water holding capacity we can actually measure. So I have 3 sponges here. I have a kitchen sponge like the orange one, and I have the yellow one like the very big pore one, and I have a white sponge which has very, very small pores in it, very small. So it's actually, and I kind of tried to cut them so they're equal volume, because that would be important. More volume, the more water. So I'm going to do the same thing we did before. I'm going to squeeze the sponge underwater. We'll start with the kitchen sponge. Let it come out underwater, and we're going to see so that's the amount of water that's being drained by gravity. The big pores are basically not, letting their water go through the sponge, until we get to a point where water is being held so tightly in the sponge that gravity cannot pull it away. And we want to measure, so this again, if you recall, this is field capacity, where free water is drained away via gravity. That means the water in the big pores. And what's left is water in the smaller pores, which is being held by adhesion, by the adhesive forces against gravity. So let's measure let's get this out first. Measure what was held in that sponge until I can't squeeze it anymore against gravity. And this is what is called the available water holding capacity. I'm just going to make it slightly pink so you can see it in the graduated cylinder. And we see we have 90 milliliters of water. Okay, let's look at the other sponges. We can predict, if that orange sponge has really big pores, that most of the water will be moved by gravity, and we wouldn't have as much held by adhesion after that. Well, we'll see, because this is science. We're going to squeeze the orange sponge underwater, let it fill all the pores with water, and then we're going to let it drain by gravity until we have no more water draining via gravity. And then all the water in the sponge is held by the adhesive forces of a solid surface to water. So here we are now. We're going to squeeze this sponge, which has the biggest pores, into this tray. We're going to color it so you can see it. I'll take this other graduated cylinder. I'm going to pour the water into this. So here we see that the available water holding capacity is much less, because the big pores are allowing water to move via gravity. And so we have about 60 milliliters of water here, versus we had 90 in the medium size, the sponge with more pores, more smaller pores, I should say. Now the third sponge is this very tight, very small pored sponge, which I'm going to squeeze underwater. Let all the air out. Let the pores fill with water. And now I'm going to, so very little actually is pulled via gravity because all the pores are very small, holding the water to their solid surfaces. Let's see how much water this sponge holds. And you predict that this would be the one that has the most water holding capacity because all those small pores are holding water very tightly. So let's measure that. So now we're at 120 milliliters of water for the sponge with the very small pores, or the soil with very small pores, which is a clay or silty soil, where you can say that the green sponge would be more like a sandy loam, had more sand in it, bigger pores, and the orange sponge would be mostly like a sand, have very little water holding capacity. All this is doing is telling us how these soils act in regards to water movement, and water retention in terms of what the plant's going to use for available water holding capacity.
This has been a production of Cornell University, on the web at cornell.edu.